This conference will now be recorded.
Okay, so now we'll be starting off with the low power verification training. So first, let's start off with the agenda. So initially, we'll be starting off understanding what is the need for power management in SoCs. Then we'll understand some MOSFET basics. What is that in MOSFET that leads to the leakage current, and how does the dynamic power consumption happen in the MOSFETs? The MOS-based circuits. The same will be applicable to FinFET as well. Then we'll understand what are the low power techniques. Both leakage power low power technique and the dynamic power low power technique. Dynamic low power techniques. We'll discuss both the things. Then we'll also talk about how does an SoC, any design power architecture look like, and also we'll talk about one thing called as power management integrated circuit. So PMIC, both architecture we'll talk about. Then we'll touch upon power management unit, and that will talk about how PMIC and PMU interface with each other. Then we'll talk about UPF concepts. This is the agenda for overall training that we are talking about 3 weeks of training. Then we'll talk about UPF 3.1 constructs. That is the latest one we are talking about. So, what are the relevant constructs for us? We'll talk about that. Then we'll also talk about the UPF design flow. Design data flow. How does the UPF based implementation work, and how does the different elements of the UPF work? Then we'll talk about some of the power intent commands, like how do we add isolation cell, how do we insert level shifters, various things related to how do we add a power supply, how do we add a power state. All those topics we'll talk about. What are the commands and what are the options? All those things we'll talk. Then we'll understand how do we set up a test bench based on UPF. What kind of updates required in the test bench? Okay, what kind of updates required in the simulation flow, compilation and simulation flow, and also we'll touch upon how design is updated to make it low power design. Just any design cannot be compatible for low power, so there are some updates that we need to do for to make the design low power compatible. So we'll also touch upon those aspects as well. And then we'll talk about the low power simulation issues. When we run a UPF based test bench simulations, what are the issues do we face? What should be our focus area? When we say isolation cell, when we say level shifter, what is that we have to check in the simulations, and what are the issues typically we face, and how do we resolve those things? How do we debug those? And then we'll take one design. We'll have two projects, one done by the trainer. I will be doing the project myself from scratch. Let's say memory controller. We won't be developing the entire test bench, system verilog test bench, because the 3 weeks time is not sufficient to set up the entire test bench using system verilog and UVM. Rather, we'll take an existing test bench, okay, which is based on SV or SV and UVM, and for that we'll be talking about what kind of updates that are required in the design, the updates required in the design to make it low power compatible. And then we'll also talk about how to set up the UPF. How do we partition the design into multiple uh, voltage domains, power domains? Those things we'll talk about, and how to implement UPF in that case. How to implement the UPF, and then how to use those UPFs that we have developed for individual modules to set up the UPF based test bench, and we'll run those simulations, and then we'll analyze the output, whether it is coming as per the expected behavior. So that is one thing I'll be doing. So then I'll be giving you one more project which you will have to work. I'll talk about that. It could be something like DMA controller or anything. So which you will have to work based based on the understanding. So as part of that, we'll talk about memory controller power architecture. We'll also talk about how to set up the low power verification setup for memory controller. Then we'll see how to run the low power simulations, then how to debug the low power issues. Then we'll also talk about low power assertions and the coverage. So this is the overall agenda. So now let's start off with the today's first topic, that is what is the need for power management. I mean, we are all aware that lot of applications that we use today are portable applications which are run by the battery. So the power plays a very important role where more efficiently power is managed, we are able to use the device for longer time. So because of that, power management becomes very important. uh, in that context, what are the typically user requirements would be whenever you are looking to purchase any electronic product? You look for high performance, you look for some advanced features, you look for smaller product size and affordable price, better battery life. So these three things are what will actually lead to more power consumption also. And when you need performance, you go for a high frequency up, right? Your processor will be working at a higher frequency. As it works at a higher frequency, it automatically leads to increased power consumption, because the power is related to the frequency, right? And also, to implement more features, I mean, as you implement more features, that also leads to more power consumption. And as you go for smaller product size, what happens? Per square millimeter, the power consumption increases, because you are I mean, one more thing is, what, as you reduce the product size, to reduce the product size, you are moving to a lower technology nodes like 5 nanometer, 3 nanometer, below that. So as you move to a lower technology nodes, it you reduce the oxide width. I mean, you would know, right? You have got the drain source, you have got the oxide, on that you have gate. So as you are reducing this one, this width also gets reduced. The oxide width also needs to be reduced, which leads to some kind of tunneling, and that leads to gate leakage also. There are four types of leakages which we'll talk about. So they become more and more prominent. I mean, there will be some unwanted structures that get created between drain and substrate, source and substrate. There is an unwanted flow of current that happens from gate to the substrate, which all leads to the leakage current, which is unwanted. Okay. So that is, those are all problems comes because as you reduce the product size, the leakage current increases. Okay, now it has become so significant that it is on par with the dynamic power consumption. I mean, it was not the problem in higher technology node. Let's say we are talking about 90 nanometer, that wasn't a problem. Above 180 nanometer, or in that range, it wasn't a problem. But now when we are moving to lower technology nodes, it is becoming a significant problem. Okay. So what is causing the power consumption? Okay, one is the SoCs have more feature integration and higher device density. That is one thing that is leading. And I mean, as I said, these are all the three factors which will contribute to power consumption: higher performance and frequency requirement. Because to get this, to get a higher performance and to increase, you need to increase the frequency, shrinking of area, and also what happens? Higher performance comes with high voltage. As you increase the voltage, the switching speed increases. What is switching speed? If you have a transistor, there is a capacitor at the this thing, parasitic capacitor. As you increase the flow of this current, okay, this will charge quickly. That will increase the switching, where it can go from 0 to 1 quickly. Instead of going like this, it will go quickly. So that is related to the switching, the current here, that will be increased by increasing the voltage difference. So that is the supply, that is the voltage domain we are talking about. So so to get a better performance, you are increasing the voltage. As you increase the voltage, it also leads to the increased leakage currents also. I mean, the current, leakage current also, power consumption also increases, and also parallelly the leakage current also will increase because of all this. And shrinking of area with lower technology nodes, for both CMOS and FinFET. Higher power consumption increases also the heat issues. I mean, since you are consuming more power, generating a more power in a smaller area, that also relates to leads to the increased heat issues. So that is where power management becomes very important, where you need to efficiently manage the both leakage power and the dynamic power. So that is something we'll talk about in the next part of the slides. How do we manage those things? So now let's briefly talk about two types of power consumption. There are, one is the dynamic power consumption, one is the static power consumption. So what is dynamic power consumption is, uh, I mean, I'm sure you are able to correlate what is this. This is a CMOS based inverter. You have got this is the PMOS, this is the NMOS, and as you are aware, since it's an inverter circuit, when you apply 0, output will be high. When you apply 1, output will be 0. Output will be 0. So as you are charging, as you change it, this goes from here to here. So what is happening is this voltage level is the voltage level at the capacitor. This is the parasitic capacitance, something we don't fabricate the capacitance, it comes because of the parasitics. So when you keep it 0, what happens is, you know that PMOS will be on. I mean, if you go to the basics of PMOS, you will be aware that when you're applying 0 voltage, because of the voltage difference between this channel will be formed and this will be on. Okay. So when this is on, this gets charged. The charge gets accumulated here, and this is at the ground charge, right? No. Okay. There's a positive, there is a negative. I mean, there will be a charge accumulated on the capacitor in summary. So when you now apply the input to 1, what is happening is the same charge which is present here gets discharged through this path, because this will turn on, this will turn off. So this leads to the loss of charge, right? I mean, whatever was coming from here, it is not going back to that, it's rather going back to the ground. So that power is getting wasted, right? The power is getting consumed where it is not coming back to the source, it's coming back, going back to the ground. So that is something that is getting wasted. That is the dynamic power consumption we are talking about. I mean, if you talk about, though for one inverter it may not be significant, but if you talk about billions of such transistors, so then it's a very significant power we are talking about. That is the dynamic power. Can we avoid dynamic power? We cannot do that, because that is the fundamental principle of the transistor based circuits. You have to charge and it have to discharge to get the logic levels of 1 and 0. Okay. So there is no concept of the charge being given back to the PDD. That doesn't happen. So there is other type of power consumption that happens in the same thing. In the dynamic power only, there is something when you are switching, there is a period of time. See, the switching don't happen like 0 1 immediately, or 1 0, it won't happen immediately. Mm. It'll happen a point where it goes through a ramp, comes down a ramp. So when it happens, there is a period of time where both PMOS is also partially conducting, NMOS is also partially conducting. So there is a path that is established between VDD to VSS. That is, the VSS is the ground, VDD is the voltage supply. So this also leads to one power consumption. So dynamic power has basically two powers. One is indicated by the red arrow, red line. One is indicated by the green line. Then we have leakage current. See, as you understand the design of the CMOS, the PMOS and NMOS, you will see that there are different types of leakage current that happen. The leakage that happens at the transistor level, okay, the leakage that happens at the capacitor level. So there are different types of leakages that happen. So we'll be talking about what are those different types of static power as well. There are four types of leakage currents. We'll talk about all those things, and we'll also understand what is the relevance of all these things for our course, because finally our our course will focus on how do we, what are the things that as a designer and as a as a design engineer that they do to make sure that this power consumption can be minimized. And how can you reduce the dynamic power consumption, how can you reduce the static power consumption? Those are the power management techniques we are talking about now. Okay, so dynamic power is only happens when you are switching, when the switching is happening. Leakage power is permanent. See, when you, let's say, keep it in high, when you keep it in low, this also won't happen. There won't be any leakage, there won't be any power consumption. I mean, if you hold it for 1, if it is held for 0, output is held for 0, this red power consumption won't happen, this green also won't happen, because it is in a stable state where there is no flow of current involved. So because of that, neither this one nor this one will happen. That power, both this power consumption will come only when you are switching. That is, you can call it as switching power consumption as well, or that is the dynamic power consumption. Static power consumption is the bigger problem here. even when you don't do anything, even when you don't do anything, uh, okay, there will be some amount of leakage that is happening. Even that is something you can see in your mobile phones also. Let's say you keep your mobile phone without using for 2 3 days, you will see the battery would have got drained. So that is the kind of leakage we are talking about, because some unwanted leakage will always be there. So that is one of the things we need, it needs to be addressed in the lower technology nodes. Next. So let's talk about dynamic power, switching power, charging and discharging of the load capacitance, short circuit power consumption. What is short circuit power consumption? This is the short circuit power consumption we are talking about. Switching time where both PMOS and NMOS are on. I mean, though we are talking about MOSFET, the similar concepts will apply for FinFET as well. Okay. You might be aware that FinFET and MOSFET has a lot of concepts similar. It just the way the MOSFET is designed is what makes it FinFET. Okay. Talking about static power, it is the sub-threshold leakage. There are four types of leakage currents are there. One is the sub-threshold leakage current. One is the gate leakage current. One is the gate-induced drain leakage. One is the reverse bias junction leakage. So what I feel is we don't need to go deep into all those things because we are not working at the transistor level. I mean, we don't need to go into analog circuit level. I mean, for us, understanding the basic concepts of different types of leakage would be sufficient. Only thing is, we'll keep it little focused on mathematical aspects. I mean, what is the total power? Is the sum of dynamic power plus the static power. So the dynamic power, as you see, is related to the square of the voltage, the capacitance what you have, this one, and the frequency of operation. So one of the things in dynamic power is related to square of the voltage. It is directly related to the frequency and the capacitance. And then you have got another thing which is the switching circuit power consumption, sorry, the short circuit power consumption. Okay, I think this is the time for which short circuit happens. I mean, for what is the duration for which that both PMOS and NMOS are on. And what is the peak current, and what is the VDD, and what is the frequency at which we are operating. So those things are what leads to one more power consumption. Okay. Then we have got a leakage power, which is the simply a multiple of VDD into I leakage. I leakage is a one, though it's a one term, it is sum of all these things actually. So we can summarize the power, total power to be like this. So as you are aware, I mean, this is a very important equation for us also to understand the further sessions. It is in one aspect that switching power is square proportional to the square of VDD. That means as you increase the drain voltage, the voltage that you are applying to, between the drain and the source, it leads to power consumption in the square manner. Okay, and as you increase the frequency, the power consumption increases. So these are few things you should remember. So though there are other equations, I mean, how the transistor width, how the transistor channel length, they impact, but let's not go into all those things. Okay. And then we have got the leakage current. Okay, so there are, one is directly proportional to VDD, in one case square of VDD, here. Then it is also related to the frequency, then it is directly related to the leakage current. So this is called as switching power, this is called as short circuit current related power, this is the leakage power. So dynamic power and the static power. Okay, so before we go into low power techniques, let's talk briefly about MOSFET, because it's important to understand what are the operating regions of the MOSFET, like what is cutoff region, what is linear region, what is saturated region. That will give us an idea about how the power consumption is related to the supply voltage, I mean the VDD, VSS, I mean VDS voltage, all those things, though partly it has been captured in this one. Okay, but let's still talk about some of the basics of the MOSFET operating regions. Okay, so for our convenience we'll take an example of NMOS transistor. Okay, so you would be aware that NMOS has a P substrate with n type of doping for source and the drain. Then it has got a oxide, then it has got a polysilicon, which is connected through the gate. Then you see in NMOS, you would be aware that source is connected to the ground and drain is connected to the voltage supply. And you would be aware that as you apply voltage here, what happens when you're applying a positive voltage? Means you are bringing the voltage difference between these two. The channel gets formed, okay, which at one point when it reaches a point where enough negative charges are accumulated, when enough electrons are accumulated here, they are attracted, okay, because you are applying a positive voltage, it becomes some kind of capacitor kind of circuit. uh, because of one side it has got a positive charge, it will attract the electrons, and then this channel gets formed. That's a very basic thing. So when that channel gets formed, because of the voltage difference between the drain and source, and you are establishing this channel, the current starts flowing from drain to the source, okay. uh, these are the things which we will talk when we talk about the leakage also. There are different types of leakages we'll talk. One is the leakage that happens here, one is the leakage due to this one, leakage due to this one. So those are the four leakages we were some among the four leakages we talked about, okay. You know that modes of operation depend upon, I mean, what mode of operation we are depend upon, whether you are in cutoff, whether you are in saturation, whether you are linear, depend upon the voltages that we apply to the gate, drain, and source. Now in that we use some different terminologies like VGS, VGD, VDS, okay, which is related to basically VGS is VG minus VS, VGD is VG minus VD, and VDS is VD minus VS, which is essentially VGS minus VGD. I mean, you do the subtraction of these two, what you get is that one, okay. Okay. And the source and drain are symmetric diffusion terminals. By convention, source terminal is at a lower voltage. I mean, in NMOS, source terminal is at a lower voltage, drain is at a higher voltage. NMOS body, that is the substrate, is grounded for simpler designs, though it need not be always grounded. It is one of the power management technique where they can change this voltage to impact this leakage current also. That is also possible. That is one of the techniques which we will talk about. Okay. There are three regions of operation: cutoff, linear, and saturated. But before we go into understanding cutoff, linear, and saturated, let's briefly talk about uh, how does this, what are the three operating modes in NMOS structure. Okay. Uh, okay. So as you can see, there is a mode where this is you applied a your voltage, you have applied a voltage which is less than the threshold voltage, so you still haven't accumulated any electrons here, first thing, okay. Then you are depleting, you are doing the depleting of the region where the, because you are applying a positive voltage here, that will repel the holes, and they will, this region will be depleted of the holes. That is what we are calling as the depletion region, okay. And then you have got the inversion where this region gets inverted by having the electrons here. So that is where the connection gets established between the drain and source. So how we, I mean, how is it related to the gate and substrate voltage? Is that gate to substrate voltage is VGS. This is the gate and the source voltage. It's a mistake. Okay. Okay, so one is the accumulation region, one is the depletion region, one is the inversion region. So when the V gate to source is less than V threshold voltage, it will be in the accumulation region. When the gate to source voltage becomes equal to threshold voltage, even that much voltage is applied, okay, then this area gets depleted. When we increase VGS above VT, then here the inversion happens where n type electrons will get uh, electrons will be reflected here. So there is a region where the current increases linearly as you increase the VGS, but there will come a point where it will get saturated. It will get saturated, beyond which even if you increase the voltage, when even if you increase the gate to source voltage, it won't have any increase in the number of electrons. That point is what we call as the pinch off region. Okay, so we'll talk about all those aspects as well. Okay, so what is the threshold voltage? It is the minimum voltage required to create the depletion region channel. Okay, um, then VGS is greater than VT for the current to pass from drain to the source. So this diagram is a little important for us to understand, because this talks about what is meant by a voltage domain in the SoCs. You will be coming across designs which are multi-voltage domain designs. So this diagram has little significance for that. So let's try to understand. So in the previous slide, I was talking about three regions of operation: cutoff region, linear region, and saturation region. So cutoff region is where your gate to source voltage is less than VT. Uh, Linear region is where the drain to source region is source voltage is less than VGS minus VT. The saturation region is where VDS, the drain to source voltage, is more than VGS minus VT. So these are the three regions we are talking about. Okay. Now, if you take a look at this diagram, can you take a look? As you can see, there are three regions here. One is cutoff region. There is where there is no flow of current happening. One, there is a triode region, which we can even call it as linear region. One we can call, one is the saturation region. So cutoff is when VGS is less than or equal to VT. So, and one more thing is this, in this graph, the x-axis is the drain to source voltage. The ID is the drain to source current, the current that is going from drain to the source. I mean, okay, that is in milliamperes, VDS is in voltage. One thing you can notice is when the VGS is less than VT, if VGS is less than VT, that is this portion we are calling as the cutoff region. Okay, in that case, it will be cut off. There won't be any flow of current. There won't be any, this line you see. Sorry, I mean, I would rather say I shouldn't have drawn here. This line itself, you see, this line itself, you see, is a point where this x-axis line itself represents this scenario. So as long as your gate to source voltage is less than threshold voltage, it will be completely cut off. Okay, there won't be any current flowing. Now as you increase your VGS, okay, uh, by let's say plus 1 volt, VT plus 1, so it leads to some amount of drain current. Okay, you see this much. As you increase it further, VT plus 2, it leads to little more increased current. Okay, so there is a relationship between VGS. As you increase the VGS, the my current is also increasing. And one more thing you will see is this, the linear region which we are talking about is related to this one. I mean, as you might see, there is a relationship between the drain to source voltage and the VGS minus VT. I mean, when your drain to source voltage is less than VGS minus VT, it will be in linear region. What is linear region is the current linearly increases. You see, it's a kind of straight line kind of relation. At this point, I mean, this point, and this point, these things gets saturated, because beyond that, even if you increase the drain to source voltage, the current will not increase further. Okay, I mean, even if you increase the drain to source voltage, this is an important thing. Even if you increase the drain to source voltage beyond that one, my current is not going to increase, because it gets saturated here. So that saturated thing is somewhere related to the gate to source voltage. You can see it is related to the gate to VGS voltage. So for us as a uh, digital design engineer, for us the important point will be two things. One is the cutoff region, and we'll be more interested in saturation region. At what point does it get saturated? So this defines the three regions of the NMOS. Okay. So is it clear to everyone?
Yes.
Okay. So for a digital engineer, the region of interest will be the cutoff region where the transistor is off. See, as a digital engineer, we'll be talking about two things. One is the logic zero, one is logic one. So the logic zero corresponds to the when it is cut off, the transistor is off. The logic one corresponds to a saturated region where the transistor is on. So these are the two regions which we'll be talking. This area, the linear region, I mean, how it increases, how much it increases, that would be more region of interest for the analog engineers. That is where when they talk about all those transistor based circuit, they will be more interested in this part of the regions. Okay. For us, we are interested in what is this point where the saturation happens. Those things would be our area of interest. Next. So having discussed some basics of MOSFET, now let us move into understanding the uh, impact of the technology shrinking. I mean, when we say technology shrinking, the moving to a lower technology nodes of the MOSFET and FinFET. So how does this technology shrinking impact the threshold voltage? When we say VT, we are referring to the threshold voltage here. As the channel length is reduced, the threshold voltage reduces. Okay. So why does it reduce? We'll discuss. It reduces because going back to this one, as this is reduced, this width of the oxide also needs to be reduced because it's the overall dimension. There is a that's a requirement that as it is it reduced, oxide thickness is also be needs to be reduced. As it reduces, what happens is your amount of voltage that you need to apply to form a channel here won't be high, right? It'll also reduce because you are reducing the oxide width. But then it leads to unwanted effects where the there is something called as quantum mechanical tunneling, which will be coming into picture, and that leads to more increased impact of the leakage currents. Okay. So the one is threshold voltage reduces, uh, which would mean that it requires lower gate voltage to turn on, which can lead to faster switching speeds. So one advantage we get is what? With the reducing channel length, switching speed will increase because you're able to turn on the transistor with a lower gate voltage. That means what? At lower gate voltage itself, the transistor will turn on and it can enter into quickly, it can enter into the saturation region and it can start conducting the current. Okay. But it also increases the leakage current due to thinner oxide layer involved in scaling down the device size. What is the drawback? It's the same thing I have written here, where as channel length shrinks, the electric field from drain can influence. See, whatever electric field from the drain, see, drain also has a voltage, right? That will also lead to some kind of channel formation. That can also lead to channel formation. Not only the this one, the gate can influence the channel potential. I mean, not the channel formation, it can impact the channel potential more easily, further lowering the threshold voltage and causing issues like drain induced barrier lowering. So there will be some other unwanted impacts. That is what we call as short channel effects in CMOS technology. There are various things. One of them is drain induced barrier lowering will happen, which is basically that whenever we are saying this term, we are talking about one more thing that leads to the leakage current, that impacts the leakage current. While a lower threshold voltage enables faster switching, summary is what? While it enables faster switching, it also leads to increased sub-threshold leakage current. You remember we talked about I sub, one of the thing called as I sub, that also increases, which can impact the power consumption. Impact of technology shrinking on the static power. As the channel length reduces, the leakage current increases. See, this I leakage will increase significantly, increases exponentially. That is more important here. So as it increases, this component becomes more and more significant in the power consumption. So now what is happening is, uh, just to compare technology scaling with respect to the power, as we are moving from 250 nanometer to 50 nanometer and further down, you see The leakage current is represented by this color. This one is represented by light brown color, the dynamic power. At 250 nanometer, there was almost no leakage current, leakage power. Here also, as you move from lower technology nodes, the leakage power is getting more and more significant. That is, at 90 nanometers and below, leakage power management is essential because it is becoming significant part of the total power consumption. So thinner gate oxides have led to increase in the gate leakage current and subthreshold leakage current, drain induced barrier lowering, all those things. So essentially, technology scaling, is it a boon or is it a curse? I mean, it should be done for voltage and threshold voltage to gain the performance. Okay. The leakage current increases exponential. Leakage power is catching up with the dynamic power. This diagram is what summarizes how the leakage power is becoming significant part of the overall power consumption. Next. Further to it, uh, this again shows, I mean, how in terms of power numbers, power dissipation numbers itself, it's showing per 100 square mm of the chip at 16 nanometer. I mean, beyond less than 90 nanometers where we are coming. You see that at 16 nm, almost both static power consumption and dynamic power consumption is matching. Now you can think of what might be happening at the 5 nanometer and 3 nanometer technology nodes, right? I mean, it could have been almost double the dynamic power itself, the overall, the component of the leakage power. That is where the power reduction techniques becomes more and more important at a lower technology nodes. And that is where you will see companies giving lot of emphasis on power management techniques. Okay. And this shows how the frequency and power are related. I mean, you know, right? In one of the earlier equation, we have already seen that power consumption is also directly related to the frequency of operation. Though leakage current don't have anything to do with frequency. Leakage current don't have leakage, static power don't have anything to do with the frequency, but the dynamic power is related to the frequency of operation. That is something that has been captured in this diagram. So you see here, this shows one of the earlier chips, Exynos 5433, which uses A57 cores. In that, if you use one core, two cores, three or four cores, I mean, this like quad core, okay, single core, dual core, like that. Okay, so this shows as you increase the frequency from 700 megahertz to 1900 megahertz, the power consumption is increasing. This is the power consumption in the watts. So when you are working with four cores at 1900 megahertz, the power consumption is almost 7.39 watts. Though for us it looks very small number when we are talking about 250 watt, I mean, kind of appliances which we use, the for 500 watt, 1000 watt appliances which we use at home. But they are all, you see, they are all powered by external source. They are not battery powered. But when we are talking about mobile phones and those kind of portable applications, this level of power consumption is very high because we are looking for a long battery life, all those things, right? So that is where the frequency also plays an important role. So now what has been done to address it? That is where you will come across called as ADVFS, adaptive dynamic adaptive voltage, DA, dynamic and adaptive voltage and frequency scaling kind of techniques will be there, where when when the application doesn't require a high performance, we can cut down, I mean, we can reduce the operating frequency and we can reduce the operating voltage to ensure that the power consumption could be reduced. For example, same four cores, instead of operating at 1900 megahertz, for example, which is leading to 3.7.39 watts. If I can reduce it to, let's say, 1200, it will reduce to one third of the one third. The same four cores will work at a power consumption of 2.52 watts. So this is what we will call it as a frequency scaling and voltage scale. I mean, this relates to the frequency scaling, how we can do the frequency scaling to reduce the power consumption. The same thing will apply for other things as well. I mean, other number of cores as well. Okay. So now let us talk about the low power techniques. So now we'll get into the core of our training, that is the UPF and how UPF is related to the low power techniques. Uh, so we'll talk about two types of techniques here. One is the leakage power reduction techniques. One is the dynamic power reduction techniques. So the leakage power reduction technique, there are various techniques. One is the power gating. So what is the power gating is, if you want to save the maximum power, what do you do? If you don't want any leakage at all, you cut down the entire voltage. So you get the power to that block. So what does it do? There is no scope of any leakage at all in that case. Second is what? Threshold voltage scaling. As you increase the threshold voltage, your the transistor leakage will be reduced automatically. Okay. Adjusting the threshold voltage of the transistors. I mean, one of the very important techniques used in all these power management techniques is when you don't want performance, you are not very particular about performance, but you want to reduce the leakage current, we'll always go for high threshold, high VT transistors. That is where even in physical design and all those things will come, they will use the terminologies like uh, low VT transistors and high VT transistors. So we'll use high threshold voltage transistors, high VT transistors when we want to reduce the leakage current. Okay, low VT transistors to increase the performance. How it will increase we have already discussed, because when you reduce the low VT, it will increase the switching. I mean, it will, at lower voltage itself you are able to establish the channel. So the capacitor at the gate output starts getting charged quickly. So hence it results in faster switching. Okay, that is where the performance will increase. So this concept is important. When your primary requirement is to reduce the leakage current, we go with high VT transistor design. I mean, you may even have chip. It's not like entire chip will be on low VT transistors and entire chip will be on high VT. It's a combination of low VT and high VT. So as we go forward, we'll discuss where do we use low threshold voltage transistors and where do we use high threshold voltage transistors as well. So one of the techniques for leakage power reduction is what? Threshold voltage scaling. The other one is drain gating, controlling the drain voltage. By controlling the drain voltage also, you will be able to impact that. Right? We have discussed about something like drain induced barrier lowering. So there are multiple things. So one of the things that can be done is to do drain gating. And then we have got reverse body biasing. Right, you apply some amount of voltage to the substrate, that is to the body of the transistor. Through that also you can impact the amount of leakage current that happens. I mean, if you go back to the very beginning of the slide where we talked this one, when we apply some voltage here, this here whatever leakage happens here could also be controlled, because you are reducing the voltage difference. As you reduce the voltage difference, that leakage current also could be reduced because of that. Okay. That is called as reverse body biasing. Then we have multi threshold voltage design. Okay, using different threshold voltages for different parts of the circuit. Then low power SRAM design. I mean, optimizing the design of SRAM. I mean, individual SRAMs itself can be optimized, because the SRAM is what goes into the memories, right? So that SRAM design itself can be optimized to minimize the leakage. So though there are many leakage power reduction techniques, not everything can be implemented by the design engineer. I mean, some of them need to be taken care at the fabrication level, those things. I mean, as a design engineer, there are few things only he can control. One is the which he can decide which part of the design should be on high threshold voltage, which part of the circuit should be on low threshold voltage, and when to do the power gating. So these are the few things which could be controlled by the design engineer when he is implementing the overall design. Okay, in summary, few techniques that could be used during the chip operation. I mean, just to summarize, There could be another, going back here, there could be few more things that could be done to control the leakage power, but not everything can be done by the design engineer when we are developing the SoC. Some of them need to be taken care at the fabrication level. Some of them need to be taken care at the transistor modeling itself, the way you are modeling the transistor. Okay, so what is that can be controlled? One is the multi voltage. You can develop your design with multi voltage domain, where you have some part of the design is working on one voltage, some part of the design is working on a different voltage. So that is one thing that can be done. Let's briefly talk about what does multi voltage domain refers to. If I show, this is my transistor. Okay, here a capacitor is there. Okay, and this is the gate, let's say this is the drain, let's say this is the substrate. Okay, uh, no, sorry, I'm talking about, it's a mistake. It should have been this one, it should have been drain, it should have been the supply. Okay, because I'm talking about PMOS here. So in this case, what is multi voltage refers to here? Does it refers to the, I mean, let's say if I have a design which has got one block which is working at 1.2 volts, one block which is working at zero 0.9 volts, one block which works at 1.5 volts. I mean, blocks means not the transistors. All the transistors inside that will be working on that voltage. Here, all the transistors in this block will be working at 1.5 volts. So when we say 1.2, what exactly is 1.2 is referring to? Is it referring to the gate VGS, or is it referring to the drain to source voltage? What do you think is it referring to? And is it referring to the voltage that we are going to apply at the source? What do you think is it referring to? It is the drain voltage. Yeah, please tell me.
Yeah, it's a drain to source voltage.
It is the drain to source voltage we are talking about basically. So now you have already seen, as you increase the drain to source voltage, it leads to increased flow of current, and that's something we have already seen when I have shown you the operating regions, right? Cutoff region, the linear region, and the saturation region. Even in saturation region, as you increase the drain to source voltage, it leads to the increased current, but there is a point where it gets saturated. Anything beyond that, if you apply, it's not going to have any impact. But you can design your circuit in such a way that where some part of the logic will be working, will be able to support at a higher drain to source voltage as you reach that level. See, let's say 1.5 volt, it doesn't mean that if I make it, let's say 3 volts, it is not going to impact the performance significantly, because that part of the block is optimized to work at 1.5 volt. Beyond that, if you apply also, it may not have significant impact, because if you go back to the diagram where I had shown you the different regions of operation, where is that? Here, once you cross VDS, once the VDS is increased even beyond further, even if you increase VDS beyond that, it is not going to increase the this thing much. See, you see here, as you increase your VDS beyond this limit, beyond this point, it is not going to impact. My current will remain same. Okay, but as you reduce beyond this, at this point, as you reduce little further, it will lead to the reduced current. Okay, which can, I mean, what is the technique that can be used for? It can be used for adaptive voltage scaling, where adaptive voltage scaling is what? As you reduce the drain to source voltage, it can lead to a lower power consumption. So in this concept we have to understand. What is one thing is that when we are talking about multi voltage domains, in multi voltage domains, we have voltage being applied at gate, voltage being applied at drain to source also. So the multi voltage domain refers to the drain to source voltage, uh, which is applied to the different all the transistors present in that specific block. Okay. So one of the techniques that is used for leakage power reduction is multi voltage designs. Um, then multi voltage with power gating. So what do you think multi voltage with power gating refers to? Can someone tell me? So here you have got multi voltage domains wherever you don't want, when so there is a particular operation where you don't want some block to be functioning because your current applications don't need that block functioning at all, so you can do the power gating. Means you cut off the entire power supply. So when you cut off entire power supply, there is no static power consumption and there is no dynamic power consumption, because there is no flow of current itself is happening, and the capacitors itself don't have any charge, so there is no possibility of the leakage at all in that case. Then you can do multi-voltage domain power gating with state retention. Mean when you are anyway doing power gating with having multi-voltage domains, you do the state retention. What is state retention is, there will be some important registers in every design. Every time you bring up that controller, I mean anytime, let's say you have for example USB controller. USB controller will have some configuration registers, which you need to configure whenever you want to bring up the USB controller for your functional operations. That time, instead of processor again configuring those registers, you can retain those values into some retention logic, and whenever you bring up that controller, USB controller, out of power collapse, you can restore those values. You basically you're saving those register values into some retention block. Once the USB controller comes out of the power collapse, you are retaining those values, you are restoring those values, saving and then restoring. So that is also one of the technique, though it is not directly related to low power reduction techniques, but that's something we will be talking about. I mean, that is an important part of every chip, because we are always looking for, we don't want just the low power, we want high performance with low power. So how do you get that high performance? You have to introduce some techniques called as state retention, that will give you the ability to bring up the a specific block operation quickly while having a low power consumption. Like examples, you're keeping a laptop in a sleep mode, where whatever work I was doing, let's say I close the laptop, it goes into sleep mode. Whenever I restart, it comes to the same thing, it doesn't reboot again. So what is happening, whatever some of the important information that I'm working on currently, that whole information gets saved into some retention logic. That retention logic will be present in a always on domain. In every chip there will be one thing called as always on domain. That whole retention logic will be present in the always on logic, always on domain. So whenever I bring up, because always on domain has those state information saved, whenever I apply power, whenever I open my laptop, from that always on domain, those values will be restored into my these blocks, whichever blocks that are working, and that is how they are able to come out quickly. Fourth is the standby mode with reduced VDD. I mean, where you are doing the voltage scaling, where you are keeping it in a standby mode. So these are some of the low power reduction techniques. Now let us talk about dynamic power reduction techniques. So what do you think we can do to reduce the dynamic power? So to understand that, you have to go to this equation. If you look at this equation, so this is the dynamic power we are talking about. Okay. So what are the factors that impact the dynamic power? Capacitance, of course, one thing. One is the VDD, one is frequency, one is VDD, one is I peak, one is frequency. You would be aware that I peak is related to VDD only. I mean, as you apply as per the drain source voltage, as per the drain voltage, current is related. So essentially it comes down to three things. One is the capacitance, one is the voltage, one is the frequency, one is this one. Okay. These are the two things which you cannot do much about, because it comes down to the transistor design, right? I mean, as a design engineer, when I'm implementing, when I'm doing RTL coding and all that, I cannot really control the capacitance and all that, because it goes down to the basic transistor design. So there are two things that you have control. One is VDD, one is the frequency. You can scale down the frequency, which will reduce this one also, which will reduce this one also. You can scale down the voltage, which will reduce the dynamic power consumption. What is the other thing I can do? Entirely do the power gating. When you do power gating, what happens? There is no VDD, there is no VDD, there is no VDD. Entire thing becomes what? Zero. So this is one more thing that we could use. So with this and having this basic understanding, let's see what are the dynamic power reduction techniques. That is one of the things that we discussed is what dynamic or adaptive voltage and frequency scaling, what we call as DVFS, and voltage and frequency scaling based on the current application being run. I mean, you scale down the voltage and scale down the frequency if you don't want high performance. If you want very high performance, you work at a turbo mode. I mean, with even more higher voltages and higher frequency. Higher voltage results in better performance, or but it will also lead to overheating also. So how do we reduce? Let's say my mobile is getting overheated. I'm using. You might have noticed that you do some intensive activity on your mobile. So what will happen? It will get overheated. So what do? Your mobile phone itself gives you indication that it is overheating. So what do you think it is doing in the meantime? It has got some kind of sensors will be there. In on the chip there will be some kind of temperature sensors will be there. Those temperature sensors will sense the temperature and will give that indication to some power manager block in the chip. The power manager block sees that temperature is increasing, and there will be something called as PMIC, power management integrated circuit will be there. That power management integrated circuit gets an indication that the chip is getting overheated. So I need to I mean, it is working beyond the required limit. So I have to reduce the voltage. So it sends a reduced voltage to it. Okay. That is about adaptive voltage scaling. PMIC block doesn't control the frequency. Who controls? Who in the chip can control the frequency? What is the component that can reduce the frequency that we generally use to reduce the frequency? It is the PLL. There will be some kind of phase lock loop, which are used to generate a low frequency clocks. So essentially, to reduce the voltage, we give an indication to PMIC, okay, power management integrated circuit, which will send a voltage with a scale down, cut down voltage. So as you reduce the voltage and as you reduce the frequency, automatically the amount of power consumed will be reduced, and that leads to the automatically lowering of the temperature. That is what essentially happens even in your mobile and even laptop when it gets overheated. So there are sensors in the SoC, monitor the heat, sends this information to ADVFS controller. This is something that we are talking in the power management unit. That is essentially part of the power management unit, power managers. Only when SoC heat is under control, the voltage and frequency is increased again. That is about how we do the concept of DVFS. The second technique that can be used to reduce dynamic power consumption is what? Do the clock gating. When you do clock gating, what happens? There's no flow of current, right? Because you are not charging the capacitors, you are not discharging. When you gate the clock, uh, there is no what happens? There is no flow of current itself, because you're cutting off the that capacitor charging and discharging. So that is one thing that can be used. So masking the clock signals in inactive logic, whichever logic you don't need to be operational, you can gate the clock. So just to summarize whatever we have discussed so far, uh, one is the multi-voltage domain, multi-VDD. What is multi-VDD? You see here there are three domains are there. One which is working at zero point 0.9 volts, one working at 1.0 volts, one working at 1.2 volts. So the different blocks are working at different but fixed voltages. So I have already told you that this zero point 0.9 volts refers to the drain voltage. What is the voltage that we apply? That drain to source voltage difference is what we are calling as the VDD. So that means all the transistors block, in this block or in this subsystem, whatever you call it as, they will all have drain to source voltage supply being supplied at zero point 0.9 volts. This is at 1 volt, this at 1.2. So who decides, should I use 0.9, should I use 1, should I use 1.2? It is all decided based on the performance requirements. For example, I have a CPU subsystem in my mobile. So that CPU subsystem needs to provide a very high performance. So that high performance comes with a higher voltage. Again, we have already discussed how higher voltage is related to the higher performance. As you increase the voltage, that what do you say? The flow of current increases, and it leads to increased switching speed. So essentially, higher voltage is related to the increased switching speed. That leads to the improved performance. The next thing that can be done is the multi-voltage domain with power gating. Okay, here we use something called as empty CMOS also. We'll discuss what is empty CMOS. It refers to multi-threshold CMOS power gating. So here we are doing something called as multi-VDD with power gating. So this is essentially multiple voltage domains with power gating. So the different blocks are working at different but fixed voltages. Here one block can also go on or off, called as power gating. But when you do power gating, you want to cut off entire supply to that block. So to do that, we intentionally use one high threshold voltage transistor. Wherever you are gating off that, right? Because you don't want any leakage to happen at that level. That is what we call as a power gating switch will be there. One power switch will be there. In that power switch, whatever transistor we use, it will be a high threshold voltage switch, because we want a high performance there. Sorry, not high performance, we want low leakage current there. Okay, that is where we are talking about the concept called as empty CMOS. I mean, of course, this is a multi VDD. Of course, this is a multi VDD with empty CMOS power gating. What is mean by here we are using the term empty CMOS is this design has different transistors, some with a lower threshold voltage, which are required for high performance. There are some transistors with high threshold voltage. There the requirement is not high performance. You are that gating, whatever you're getting, let's say, simple example, I have a switch in my room. That switch should be very efficient. It should not, this switch itself should not have any leakage. In my house there is a one option I am using to on and off the lights, right? That switch itself should not have any leakage. That performance comes when I use a high threshold voltage switch. Okay. But where I need performance, I'll go with a low threshold voltage switches. That is why we are using the term empty CMOS power gating. What is the third one? You do the power gating. So empty CMOS applies here, multi VDD applies here. They will all be there. Okay, but you do with a state retention. What is that? Different blocks are working at different but fixed voltages. One block can go all same thing as till last point. Here registers and sequential block value of shutdown block, whichever block you are shutting down, are retained in retention registers. They're saved into the retention registers, and then you can restore whenever you bring up that block. Then the fourth one is the interaction of the power controller for adaptive, dynamic and adaptive voltage and frequency scaling. So here what is happening? This entire thing will still apply. All these concepts will still apply here. But you are doing further power control by using dynamic adaptive voltage frequency scaling. So we can even call it as DVFS, DVS, AVFS, AVS. So all of them essentially refers to the similar kind of concepts that we are talking. Okay, here blocks of a system can switch between two or more voltages. Means here what is the point is this block, okay, the violet block what we are talking, which was initially designed to work at 1.2 volts. Now that could be designed to work at, design means what, it will essentially work, right? See, if, for example, I have a light in my house, this room, which is supposed to work at a 230 volt supply, for example. Will it not work if I give 180 volts? It will still work, but it will work a little dim. It won't give me the same amount of this thing what I generally get. But for a specific requirement, I'm okay with that. Let's say at 1.2 get 1.2 volts, I get high performance. At 0.9, I don't get the same level of performance, but I'm okay with that. But on a positive note, what I get as an advantage, I get a reduced power consumption. So that is where you can do the voltage scaling. That is what we are calling as the dynamic voltage scaling, okay, or adaptive voltage scaling, uh, which will be done by who? Power controller. And who will control the power controller? No. PMIC won't control. It's the application which will control. I mean, it is controlled by the operating system. See, everything is finally controlled by the operating system. The operating system knows what kind of application is being run. Is it a high performance application? Is it a low performance application? That would in turn control the registers in the power control. The power controller sends an indication to whom? PMIC, saying that I want the voltage to be reduced because it's a low performance application. That will in turn, see, PMIC is the block which generates voltages to the chip. For example, in my mobile also, there will be a PMIC block will be there. PMIC is the one which is getting the power. Okay. I mean, it is the one which generates voltages to the different blocks of the chip. So what does it do? Instead of sending the 1.2 voltage supply, now it will do what? 0.9 voltages. Okay. Then it will start working at a lower reduced voltage, which essentially leads to the lower power consumption. Okay, blocks of system can be switched between two or more voltage voltages depending upon the loads and depending upon the closed loop which is used to adjust the voltage. Let's understand what is the meaning of empty CMOS power getting. We have already discussed empty CMOS means what? Multi-threshold CMOS means a design having transistors of different threshold voltages. Okay. So why we are using empty CMOS power getting means these high threshold voltage transistors are used at the power switching point. Like these switches in my house, they will always be, you can think of them to be having high threshold voltage so that there shouldn't be any leakage from that. Circuit where few CMOS have one threshold voltage, other CMOS have different threshold voltage. For high performance use low threshold voltage. For to reduce the leakage current use high threshold voltage. And what happens is, I mean, this is talking about the power getting logic. In power getting, what happens is there will be one physical VDD line will be there. In between switch will be there. This is the power switch. When you turn on, this connection gets established. When you turn it off, this connection is lost. This we are calling as the physical VDD. This we are calling as the virtual VDD. This one. So there are, I mean, it's not very important as such. Just understand that what goes inside into the chip is the virtual VDD. What comes from the PMIC is the physical VDD. When this connection is turned off, when you turn off the power switch, right, virtual VDD will go off and automatically there is no supply voltage, there is no drain voltage, so there won't be any dynamic or there won't be any static power consumption. So entire logic connected to the virtual VDD goes off. Some more low power techniques. Here let's talk about the basic example of a written. Yeah.
Sir, the relation between threshold and high performance, right? Little bit confused.
Relation between threshold.
Means high performance, low threshold, like that.
One second. Relation between threshold voltage VT and performance. Okay, let's understand that. See what happens. You know what is the threshold voltage? Please tell me. The minimum amount of gate voltage that you have to apply, VGS that you have to apply to establish the channel, right? To create the depletion region. Once you create the depletion region, then the channel is established and the flow of current will happen. Now, as you reduce the VT threshold voltage, what happens? Let's take an example here.
If small current flows also, it will.
No, not small flow of current. I'll tell you easy to understand it. Take the same. So where is the inverter circuit? I had inverter here. Okay. Let's take this example. See, there is a connection between this one, right? I'm just taking this to show you. I mean, it won't be that inverter is connected to inverter. Basically, one logic gate is driving the other logic gate. That's how you can think of, right? The output of this will be driving another logic gate, and all of them will have the driven by same VDD. See, this is the same VDD we are talking about, right? Now, if this transistor, and this transistor is a low VT transistor, what happens as you charge this one? This is a ground voltage, right? You know that this is the ground. So as some amount of charge current comes, as the current starts flowing, as soon as it hits specific voltage level, this will turn on, that whatever, turn on or turn off, whatever, right? Essentially that will I mean, you take essentially the point you have to understand is, when you have the transistors with a low threshold voltage, these will get charged. What will happen? This will turn on quickly. Again, what will happen? This will get charged quickly. The overall circuit performance increases, right? Now take the opposite side, where the threshold voltage is high. What will happen? It will take lot of time to turn on them, because this capacitor need to charge for a much longer duration. Only then you will see that voltage difference. Right? Capacitor doesn't get go from 0 to 1 immediately like this. It goes like this. So we are talking about whether this is where the low VT transistors will turn on, this is where high VT will turn on. So this is the timing difference. So here the switching speed is very high, right? Here it takes so much time to switch the transistors. So that's the relation. Right. Now these are the VDD we are talking about. See, VDD VSS. What exactly is a VDD VSS is? So let's start here. Now, this VDD, this blue line, is the voltage domain, represents the voltage domain. And when we say 1.2 volt voltage domain, this blue line is powered by 1.2 volt. Where does that 1.2 volts will come? PMIC. What about this ground voltage line? Right? It will be at 0 volt. And where does it again comes from? PMIC only. See, because even ground need to be connected, right? Even in your house, we need to do the proper grounding. The same thing. You can think of even your chip to be like a house connection only. The way you have the power connections in house, you can think of like that only. Okay. Okay, you got it right. So because of that, this switching is happening, which is in turn impacting the other transistor behavior. Okay. Um, 1 second. I'll just. Any questions in this? Let's go back to. We talked about this one. Okay, we talked about this. Empty CMOS getting we have discussed. Okay, virtual VDD we discussed, and the other low power. Yeah, we were talking about the retention example. I have already told you it's a very simple concept. What is a retention example? Where does this whole retention comes into picture? Is if you take any SoC, what is an SoC? processor subsystems, some CPU subsystem, plus some interconnect, plus some lot of controllers, and then you have power management units and some various things. I mean, let's not go into all the things. Most important thing we are talking about is the lot of controllers are there. What are the controllers we are talking about? We are talking about USB controller, DDR controller, PCI Express controller, okay, Bluetooth controller, or any peripheral you have, you will need a controller for that, right? Etc. So every controller, let's say when you work on USB controller, we can't directly, USB controller can't directly interface with, can't directly start doing transfers to the USB peripheral. It requires some configuration from the processor. I mean, processor needs to configure its behavior. Only then it can start doing some transfers to the USB peripheral. So it requires the processor to run some instructions to configure its registers that are present in the USB controller. So USB controller has registers, has lot of registers which needs to be configured, and it is done by the processor, right? You see, that will involve always a lot of latency. Rather, if you have a mechanism, for example, I have a specific requirement where I won't be using for USB for some amount of time. So I can do, what can I do? I can cut off the logic where USB control is present. Let's say USB control is present in one particular domain, where I can cut off the voltage for that domain, and I can save the power. For a significant amount of power can be saved. What power saving will come? Both dynamic power saving will come, static power saving will come. Now, let's say USB controller is power down, is power gated, power collapsed. We'll use the technical terms only a little bit. Power collapsed. Now when it is powered up again, powered up, it needs to get back to the same state where it was working. Because you just temporarily you cut down, when you bring it up again, it has to start working in the same manner. So there is a need to restore the register values, so that processor don't have to do again, processor don't have to do it again. That is where every SoC has retention logic present in always on domain. There will be something called as, every chip has a always on domain. Means, what is always on domain? The name itself tells you that it's a domain. Even when you cut down everything, every voltage, every block in the chip, I mean, let's say you're power collapsing USB controller, you're power collapsing CPU subsystem, you're power collapsing PCI controller, but always on logic will still continue to get the voltage. Because it continues to get the voltage, what will happen? It, whatever information it is present here, it will continue to retain that information. So what happens? Whatever, let's say I want to restore, we may restore, we may store, we may save the 10 registers information into retention logic. Okay, now how it is done, we'll also talk about that. So when USB control is powered up, what do we do? The above registers are retained, values are, register values are retained. So it works. So that is the basic idea of retention logic. It results in the power consumption required for, but what is the negative side? To retain those values, you need to continuously power that, right? You need to store that values, you need to continuously power. So that will lead to some amount of power consumption, but that's okay. I mean, we are okay to have that, we are okay to compromise on that, because it leads to a larger power consumption, since you are cutting down the entire USB controller, and on the positive side, you are also getting the performance. See, if you take an example of CPUs, See, in the CPU subsystem, the core core might be turned off, but the logic required to bring up the CPU might be retained, which makes the CPU bring up easier. Some registers are critical for core bring up. So whichever registers uh, that need to be retained, that need to be stored, they will go into the retention logic. Okay. So which registers are to be retained, that is something designed provided by the design architect. Architect will tell these registers are relevant for this block, so these need to be retained. For example, some data values are there which you don't want to retain, you can lose them. So the architect will tell which part of the logic need to be retained, which part of the register space should not be retained. So that's a brief about retention logic. Then we talked about DVFS. See, power control can drive voltage domain 1 between zero point 0.9 to 1.2 volts. It involves latency but results in a power saving. See, what is the latency we are talking about? I have to inform to the my power management unit has to inform to the PMIC that you need to reduce the voltage. There will be one LDO will be there. PMIC will have something called as LDO, which reduces the supply voltage, where the point 1.2 comes to 0.9. LDO is low dropout.
I am working on same thing.
Okay. Okay, sure. A frequency scaling can be done to contain the temperature. Scaling can be done to contain the power consumption. Okay. I mean, one is to control the temperature. You can do the frequency scaling. One is to essentially both are related. See, these two are also somehow related, right? Power and temperature are related to each other. But essentially, this is somewhere the relation. As the temperature is increased to cut it down, they reduce the frequency immediately. To reduce the power consumption, they reduce the voltage. Now, let's briefly talk about the power gating. What exactly is the power gating? So, power gating, this is the block which is there. This is the ground. This is the supply voltage, the VDD. This is the VSS. Without power gating, this would be directly connected. Okay. Then what are you doing? You are introducing a switch. It's like we introducing a switch in our house. Why the switch is helpful? Otherwise, if there is no switch, what will happen? The light will be always on, right? Only if you have to cut down, you have to cut down the entire house power. Only you have to cut down. By introducing the switch, you're able to control when they should get the power, when the power should be cut off. But as I said, this switch need to be designed properly, right? If you Same thing, if you don't have a proper switch, it leads to a lot of problems, right? I mean, you need to choose the right switch, what amount of current need to flow, all that, right? This control, tell me who controls it. Is it controlled by this voltage or this voltage? Let's say A, B. Is it basically the switch on or off? Do we control by the drain voltage or the gate voltage?
Gate voltage.
Gate voltage, right? Because always the transistor, should it be, whether it should be in cutoff region or whether it should get into the saturated region, will control by the gate voltage. That means the power switch will have some control signal. That control signal will come from my power management unit. Some power managers will be there. They will send the control signal which will control this one. So power gating, what it does is it shuts down a block temporarily when it is not used. Shut down based on the values of the control signals. So when to shut down will be decided by the control signals. Control signals used to shut down are driven by the power managers. So there will be some power managers in the chip or power management unit, which will be responsible for generation of the control signals. Power switches are larger in size. Why you will make them larger in size? Because you want high threshold voltage. To control the rush currents. To control the rush currents and not to have any IR drop. I mean, if you have larger switches, the IR drop won't be there. I mean, the voltage drop will not be there. Okay. Power switches use high VT PMOS. Okay, this is what is used. PMOS is being used. It's a high threshold voltage. High threshold voltage is achieved by using a large channel length. Otherwise, it can result in the leakage. I mean, it all summarizes only one thing: threshold voltage should be high. This control signals comes from what? Power management, power managers. Who controls the power managers? Power managers have a registers. Power managers have a registers specific to each subsystem, each domain. Let's say your chip has 30 power domains. Assume your power manager will have 30 registers where you configure a specific value. When you program that register, that will in turn generate a signal which will cut it off. You understood?
Register programming, sir.
It'll all come through register programming only. PMIC is only like a voltage supplier, that's all. PMIC is only responsible for voltage supply. I mean, whether you want to supply 1.2 volts, whether to supply 2.0 volts, is what is the role of PMIC. PMIC don't have any registers as such to configure its behavior. It will get some kind of control from the SoC, from my power manager, or dynamic adaptive voltage scaling. Through that, it decides what level of voltage I have to give. This switch doesn't have anything to do with the PMIC. It is to do with my power manager, which is nothing but PMU, power management unit. Power management unit has some registers. Okay, by configuring that registers, you can power collapse this logic. What is as part of power collapse? What is happening? You are not removing this voltage. You are only cutting off. See, it's like till this point in my house where the switch is there. Let's say I have a switch. Till this point, power is coming. But beyond that, it's not going because I'm switching it off. Same thing is happening.
Okay. So it means PMIC is giving supply, but
PMIC is that till VDD it's coming.
coming correct.
But inside it's from here to here it's not going because you have cut it off.
Okay. That is we are doing with the register configuration.
That is through register configuration. You are generating a control signal. From where that control signals are coming? Power management unit. Power management unit has what? Some kind of registers.
Hello.
Yeah.
The CMOS logic itself is a very big logic, right? It has so many rails inside that one. How one power switch can control entire CMOS logic?
You are telling? Please repeat again.
The CMOS logic itself is a very big, right? So it has so many standard cells inside, and it has a power rails. So
Yeah,
how?
it has a that's what. So we are talking about the entire power rail itself is controlled by this one.
I mean, top layer
Okay.
power rails.
Yeah, top VDD is connected to this one.
I mean, there will be so many VDDs, right, in that voltage
No, no,
level.
no. Same. I mean, the voltage distribution will happen, right? What I'm talking here is here you will use a power switch. Here the main powers will come from the PMIC.
I mean, the same VDDs, right? There will be so many VDDs, right, in the
That's what.
control.
See, at the end of the day, there will be one point from where, see, assume this is VDD, this is PMIC, from where the let's say 1.2 volt power is voltage is coming. You'll use the power switch here, and to this entire thing you'll connect.
Okay. Okay.
Got it, right?
Yeah, hi Sreenivas.
Yeah.
Yeah, actually in the SoC we have multiple IPs and multiple sub-blocks, right? So each block and each sub-blocks have different power management systems, or how the register configuration will work. And like, are we getting the register configuration only one block, or we have different blocks, different
It
register
depends. See, how it
configuration?
works is if you talk about a complex subsystem like CPU subsystem, it can have
Okay.
multiple power managers. Each core will have one power manager. But for rest of the logic, you could have one power management unit which is responsible for the power management of the entire SoC components.
Okay.
So it is specific to the design. For example, even in CPU subsystem, there will be one power manager per core. Each core will have one power management per cluster. See, you have a cluster, right? For that cluster means what? You have got multiple cores into the same CPU subsystem, right? That itself
Yes.
will have one power manager.
Okay.
I'll still make a note of this question and I'll get back on this. Uh, Next. So this is showing you an example of the power supply that is coming from PMIC. You've got block 1, block 2. So the block 1 which is having one power switch, block 2 having one power switch. Now what is this
One
will
basic question. Sorry for
yeah,
interruption. Maulik here. So, will the block will request for power gating, or or some other logic will request based on block should
everything
not
is
use any power?
everything is controlled at the operating system level. See what will happen,
Oh,
I'll tell you. Right now my mobile is there on my table. I didn't use it for last half an hour because I'm doing the training. Okay, I
oh,
don't have any need to use it. So there is my mobile phone has the operating system which is having some drivers running inside it. The drivers are noticing that this person is not using the mobile phone for such a time. It knows that there is a 60 seconds. I mean something like, let's say, 60 seconds screen turn off time. Okay.
yes,
So when they count that much time and see that for 60 seconds there's no activity, right? The timers will be there. Some real time clock, those kind of some timers will be there. What do? They send some kind of signaling to the power management unit or some block, which in turn, uh, could result in my CPU configuring the power management unit, indicating that there is no activity for this much time. You have to you can you can put the entire block into a low power state, for example, and which would in
oh,
turn generate a signal to cut off this voltage.
yeah, yeah. Oh, okay, then. Thank you. What I was assuming is for some clocks, for some blocks, clock request will be there, acknowledgement will come. Similarly, block one might be requesting for power supply. I was
No,
assuming
it's
like that.
not the block one which will do. I mean, I alone same block cannot request to supply power and other thing. It has to be controlled at the upper level. There will be drivers corresponding to that block, which are further controlled by the which are on which there is still operating system running. Through all that thing, it will happen.
Okay, thank you.
Now, if you look at this diagram, this black box, I'll call as a voltage domain. Power domain 1. Power domain. Means what is voltage domain here? Let's understand. Why everything is a whole black box is one voltage domain? Because if this power supply is, let's say, 1.5 volts, all the transistors, everything is powered by the 1.5 voltage supply only. So that makes it one voltage domain. And what is power domain means? I'm able to control this domain's power independently by using power switches. Cutting off this voltage, see, shutting down the entire power, collapsing the entire voltage domain will be done by the PMIC. If I want to cut down the entire voltage, I can give some kind of indication to the PMIC to cut down the entire voltage. That is also possible. Right. Okay. Any questions on this? Next. Initially, both block one and block two are on. Later, for specific requirements, I mean, where does the specific requirement comes is at the from the application level only. When we say application level, the drivers that are running on top of my hardware, the embedded firmware, that will be monitoring the things, and they will generate some kind of register programming from the processor to the individual power management units. And let's say it needs to be retained. Turning off this block 2 is called as power switching. Control signals are driven to turn off the block 2 voltage. The design changes are required to make it low power compatible are called as low power techniques. When we say the term low power techniques, what is that it's talking about? whatever design changes we do to make it low power compatible. So what is that we have to do? We have to add some power switches. Okay, then when you do the power switching, there is a connection that could be happening between them. See, block 1 and block 2 won't work independently, right? There could be some signals going from here to here, signals coming from here to here. When you uh, power collapse and when it is on, you don't want this to be corrupting this, or vice versa. So that is where we have to use some kind of isolation cells. There are those techniques, collectively we are calling as the low power techniques. One of the technique we have talked is the power gating, and we'll also use the term called as level shifters. What is level shifters here is, this I said working on one voltage domain. There could be one more block which is working on another power supply, which is, let's say this is 1.5 volts. Let's say this is working at 1 volt. When a signal goes from here to here, there's a problem, right? What could be the problem? Whatever is logic 0 here, for example here, because it's 1.5, zero point 0.7 voltage is still treated as logic 0 only here, because zero point 0.7 is below the half the voltage. When it goes here, it could be treated as a logic 1. So for that we have to do level shifters. Here we'll use a level shifter which will do the linearly reduce the voltage. See, 1.5 is to 1 is what? 3 is to 2. So it will make 0.7 become 0.466. So that's the level shifters will do. So we'll talk more about what is power gating, what is level shifters. Have you understood this diagram? What exactly is it? So do you think this control signal is driven by the same thing? Is it the same signal or is it two different sources?
Can be different.
It will be different, right? Because you want to have different control for each one. It's like in this room, if I have 4 lights are there, I want to have 4 switches to control each of them. Same thing, this is one switch, this is another switch. Okay, it's like, as said, light itself won't decide when it should be off, when it should be on, right? Who decides? I will decide. How did I decide? I know that I'm not going to come into this room for next 2 hours, so I don't need any light, so I'll turn it off and go. So what is I am the application. Next, now let's talk about level shifters. You see here how many blocks are I have a CPU block which is working on 2 volts. I have peripheral block which is working on 1.2 volts. So this VDD1 is the one voltage domain. It is representing one voltage domain. Okay. This VDD2, which is powering the peripheral block, it represents another voltage domain. So which is VDD1 is at 2 volts, VDD2 is at 1.2. Why is it 2 volts? Because CPU needs high performance. Peripheral blocks don't need same level of performance. In that case, when a signal goes from here to here, I told you, right? 2 volts means what? Logic 0 is not always 0 volts. Logic 1 is not always 2 volts. It's a range that is defined. Logic 0 could mean anything from 0 to 0.7 volts, for example, or 0.8 volts. Logic 1 could mean what? Anything from 1.2 volts to 2 volts. Okay, so that 0.8 to 1.2 is the undefined region, where we can call it as metastable region. Okay, in that case, if you take an example of 0.8 volts for this domain, for the this one, that what could be the region? 0 to 0.5 could be the logic 0, 1.6 to or 0.7 to 1.2 could be the logic 1. So here the problem comes when this 0.8 voltage, see, you know, right? 0 and 1 is only for our understanding, for a digital design engineer understanding. But in the real chip, whatever happens is the current flow only. Everything that happening inside the chip is a current flow. The capacitor is getting charged, capacitor is getting discharged. Okay, so it all comes down to the current flow and the voltage getting changed. Okay, so in that case, what could happen? This 0.8 volts when it goes from here to here, when a signal is moving from here, this domain to this domain, what is the signal? It could be address signal, it could be the data signal, it could be enable signal, which is going from CPU to peripheral block, right? Because CPU will send some transactions. The transactions will have the address information, data information, the enable, the burst, like different things. So what is happening when they send? Actually, the current is flowing, the voltage is getting this current will be felt from here to here. So whatever voltage that you give as zero 0.8 volts here, okay, whatever is zero 0.8, because it was a logic 0, your understanding was what? I'm keeping logic 0 here. That is where you have zero 0.7 or point something, let's say you assume 0.7 only. Your voltage was 0.7. Your assumption was what? It is a logic 0 for you. But the problem is, if you don't use any level shifter, the same zero 0.7 volts, when it goes here, you understanding 0.7 volt I'm talking about here? Here this is in one voltage domain, this is in another voltage domain. Here whatever the voltage difference you kept as 0.7, when it goes into the other domain, it actually ends up turning it on, because these are designed for a lower voltage levels. These are designed for a lower voltage levels. They will be turning on, they will be thinking zero 0.7 volt is actually on voltage. So that means what? That will go and end up getting treated as a 1 volt here. I mean, the logic 1, sorry, logic 1. That is where the problem comes. So to avoid that problem, we use level shifters. What does level shifter does? I have already told you. What is the relation between 2 volts and 1.2? 2 by 1.2 is what? 5 by 3 relation. So if 0.7 has to go from here to here, level shifters will simply do 0.7 into 3 by 5. What is it? 2.1 by 5, it will come to something like 0.42 or something, some number roughly, right? You know. Okay. 0.42 it will go when it goes to the peripheral block. The level shifters are inserted at the domain boundary. Will there be only one level shifter? No. For every signal that is going, let's say if address is 32-bit, okay, data is 64-bit. So you have to keep all those power shift level shifters for each line that is going from one domain to the other domain. You have to keep level shifters. So level shifters will be connecting one voltage domain, will be kept at the boundary of one voltage domain to the other voltage domain. Level shifters are inserted at a domain boundary to translate from lower to higher voltage range, sometimes from higher to lower voltage range, and vice versa, right? It has to be both the sides. Translation ensures that logic value sent by the driving logic in one domain correctly received by the receiving logic on the other domain. Level shifters translate inputs with one voltage swing to another output with different voltage swing. Standard cell library will have different threshold voltages also. I mean, see, standard cell library will have, I think I don't see any reason for this statement. This should have been there in the empty CMOS topic, multi-threshold CMOS, right? I mean, what is standard cell library? It is not relevant to functional verification design engineer. It is more relevant to backend engineers. When the backend domain engineer, physical design engineer implements, he has a standard cell library available from which he uses which cell I have to use. Should I use high VT CMOS or low VT CMOS? That's the context. This is not relevant to this slide. Okay. Okay. Let us now go for a break. We'll stop